as we move into lesson 2.2, we're going to talk about this concept of instantaneous velocity and speed. Please pause the video and look at those three objectives that we're going to learn today. Today we're going to introduce the concept of calculus a little bit. It's just pretty basic calculus. If you struggle, we can do a couple of examples together. All right, the next thing we're going to talk about are two key ways to define how fast something is moving. And that's like what you would think about normally as speed, like your speed on the highway. And another word that kind of gets mixed with it but shouldn't is velocity. Because they are two separate things. Because velocity can be positive and negative, whereas speed is just kind of like the absolute value of velocity. When we ask the question, how fast is something going, we're talking about the value of the speedometer that would give. This value is known as the instantaneous velocity. So by definition, the instantaneous velocity is how fast a particle is moving at a given instant. How fast a particle is moving at a given instance. So like, for example, when my kids are in the back seat of the car and they're like, Mom, how fast are you going? And I'm like going 45 and a 35. I would say 45, but then I would take my foot off the gas and then I'd be going 35. So your instantaneous velocity changes for the exact moment of what you're doing. So instantaneous velocity or velocity is defined kind of by calculus. It is a limit as the change in time approaches zero. Now that means nothing to you if you haven't done limits in calculus yet, but what that means is you're looking for the time between 2 points to essentially be as small as possible, and that kind of is by definition the word instantaneous. So you want like time to be like really close, like that exact moment. So that in calculus is defined as the derivative of x, which is displacement, in respect to time. So you write dx over dt. X is your position, t is your time. X is your dependent variable, time is your independent variable. And in calculus, this is called the derivative. And long story short, someday when you learn about derivative, it just means the slope. So I have a star. When I was going through this, I have a star and it says the main thing. I wrote main thing to tell students. So let's write main thing. You need to find 2 points super close to each other. I'll just write find 2 points super close. And then you'll find the slope between those two things. And this way is not using calculus. When I teach you how to find the derivative, that is using calculus. It's much easier to use calculus, but we'll talk about it both ways. In words, time gets smaller and smaller. Like the change in time. Pretty much until you're within an exact moment. And the calculus way is you say it like this. You say the limit as t approaches 0 gives us the derivative of position in respect to time. The limit as t approaches 0 gives us the derivative of position in respect to time. Remember, it's just the slope. V at any instant is the slope, which is the same word as like derivative, of a position time curve at the point representing that instant. Now when you look at the next page, we have a time position graph. And if that's hard for you to kind of comprehend, T stands for time, X stands for position. Okay? So they have all these like funky little lines pointing here. That's because let's say that we want to find the instantaneous speed between like these two sets of time. I'm going to put a dot there so you can kind of see. Notice the slope of this line is pretty steep and it's positive. But now if we extend that time, notice how we can get this point and that point? It's not quite as steep. And the further out we extend it, and notice I'm just touching, I'm touching the curve. These lines are the slopes of the curve from here to that part. It's getting less and less and less steep. That's because the velocity over that time interval is getting slower and slower. Please remember from Algebra 1 that slopes can be positive, slopes can be negative, and slopes can also be zero. Like if you're not, in that moment your car stopped. Like if you're going forward, you stop and then you go in reverse. There's an instantaneous where it's zero. This proves that velocity is a vector. Please remember, vectors have like the direction of the sign and stuff. So we talked about vectors yesterday. Since these have directions, velocity is defined to be a vector because they have like a positive or a negative or a zero. Then we have speed. Speed is kind of different, right? So speed is the magnitude. By the way, magnitude is just like a number, like 1, 2, 3. It's like the numerical value of velocity. In other words, if you just like make the absolute value, so it's never going to be negative. So you're going to write absolute value of velocity. So if you get a velocity of negative 10, the speed is 10. If you get a velocity of 10, the speed is 10. All right, speed and average speed can be super different from each other because average speed is like within the whole like trip, whereas speed is the instantaneous velocity and then the absolute value. Okay, you might want to rewind that sentence to try to make heads or tails of that. So example 1, what speed associated with what speed is associated, is associated with 5 meters per second and negative 5 meters per second. So if these are velocities, the speed is just the positive value. So the first one is 5 meters per second, and the second one is also 5 meters per second. So just remember, speed is absolute value. All right, let's take a look at example 2. Now, example 2 is going to take us a while to go through, so be patient. And whenever I do these, I always like draw them out and I read them really, really carefully, okay? A cheetah is crouched 20 meters to the east of an observer. At time equals 0, the cheetah begins to run due east toward an antelope that is 50 meters to the east of the observer. During the 2 seconds of the attack, that should say attack, not attach. During the 2 seconds of the attack, the cheetah's coordinate x varies with time according to this equation. X equals 20 plus 5t squared. Find the cheetah's displacement between t equals 1 second and t equals 2 seconds. I know they skipped B, so just go to C. Find the instantaneous velocity at t equals 1 second by taking delta t to be 0.1, then delta t to be 0.01, then delta t to be 0.001, and then part D, derive an expression for the cheetah's instantaneous velocity as a function of time. There's a lot going on in this problem, and I kind of feel guilty. This example 3 should probably be on the separate page, just because this is going to take up a decent amount of room. So I'm going to write very small and trying to keep my work very, very neat. Okay, so let's take a look at what's happening first. A cheetah is crouched 20 meters from an observer. Okay, so here's our observer. I'm going to draw it over here. Go 20 meters. There's the cheetah. And he is going to run after an antelope that is 50 meters to the east of the observer. So when we think about it like this, here's our observer, here's 20 meters, here's our cheetah. Now this guy ends at, here. Let me put that 20 somewhere else. I'm going to put it right by that dot. I'll write x equals 20 by this dot. I'm going to write x equals 50 by this dot. Okay? All right, let's keep reading. At time equals 0, he begins to run. So we can even put at this little dot, we can put t equals 0. And he's going to go towards him. During the first 2 seconds of the attack, the cheetah's coordinate x varies with this. So he has 2 seconds within here where his position is this equation. Find the cheetah's displacement between t equals 1 and t equals 2. So we have this formula. You ready? So we're on part A. They told us that the position equals 20 meters plus 5t squared. Notice I just kind of took off the units. Excuse me. So x sub 1, because that's like our first spot. So they want us to ask, well, where is he now at 1 second? So we're just going to do x of 1 equals 20. In fact, this one, don't write x1, just write x, because this is our general equation. So x sub 1 is going to equal 20 plus 5 times our 1 second squared, which is going to be 20 plus 5, which is 25. And this is our position, so it's in meters. Next, they want to know where is his position after 2 seconds. So we do 20 plus 5 times 2 squared. So that's going to be 20 plus 20, so we get 40 meters. But part A wants his displacement between t equals 1 and t equals 2. So the displacement is the second one, 40, minus the first one, 25. So his displacement is 15 meters altogether. Now for part B. I guess it's part C they have. Okay, I'll probably end the video, or at least take a pause on the video after this one. We need to find the instantaneous velocity at 1 second by taking delta t to be 0.1, and then delta t to be 0.01, and then delta t to be 0.001 seconds. So we're going to find his instantaneous velocity, not his average velocity. So the first thing we're going to do is we're going to let delta t equal 0.1. So at t equals 1 second, we know x sub 1 equals 25 meters. Now, since we're going to let delta t equal 0.1, we need to let, that was the first t, we're going to let the next time equal 0.1.1. So it's like 1 second plus this itty-bitty amount of time. So x is going to equal 20 plus 5, because we haven't like mathematically figured this one out yet, plus 5 times 1.1 squared. When we put that in our calculator, I know I have it over here somewhere, 20.065. I'm sorry, 26.05. I read my handwriting wrong. And it makes sense that, you know, a little bit of extra time, he's a little bit further along. So if we are going to find the velocity at that point, we learned that velocity is the change in our x's over the change in our t's. So the change in these two x's is 26.05 minus 25 over the change in our t's is 1.1 minus 1. So we end up getting 1.05 over 0.1. So we end up getting 10.5 meters per second. We're going to do this again, but we're going to really focus in, and we're going to go even smaller. We're going to delta t, the problem asks, if you read, they want delta t to equal 0.01. So we already know that if t equals 1, we know that x equals 25. But now what we're going to do is we're going to alter that by 0.01. So we're getting even more of an instantaneous read. So we're going to let the next evaluated position be at 1.01 seconds. So we're really focusing in on that the cheetah's time is getting a lot closer. So we're going to need to plug that in to find our x. So it's going to be 20 plus 5 times 1.01. When you put that in your calculator, I already evaluated it, you get 25.1005 meters. Now that makes sense that it's not quite as big as this 26 because 0.01 is a shorter amount of time. So our velocity in that area is going to be delta x over delta t. So subtract your x's, you end up getting 0.1005. And if you subtract your t's, you get 0.01. And if you divide that out, you get 10.05 meters per second. This is not enough room for you. And again, we're going to let do here, we're going to let delta t equal 0.001 second. So we are really getting a lot faster, getting a lot closer to that instant value of his speed at that moment at t equals 1, because we're really honing in really close to 1 now. So we know at t equals 1, I think we probably have it memorized right now that x is 25. But now let's just go a little bit further in time. Let's make t equal 1.001. X is going to equal our equation 20 plus 5 times 1.001. And I already did the calculations. That's 25. Point 01 0 0, let me see, 0 0 0, so 3 zeros and a 5. So if we want to find the velocity here, we end up getting delta x over delta t, and delta x is the difference between these two numbers, so 0.010005 over our delta t is the difference between these two t's, 0.001, for a final answer of 10.005 meters per second. So what I want you to focus on is when t was 0.1, we were at 10.5 meters per second. When t was 0.01, so we were getting really closer in time, t was 10.05, so we're really honing in here on that. And then when t equaled 0.001, so like that's 1,000th of a second, we have 10.005. So hopefully what you're seeing is at first we're like, oh, it looks like it's like 10.5 miles per hour. Oh, wait, but maybe it's actually closer to 10. And oh, wait, it's actually super close to 10. So we can kind of conclude that like at that instant, at 1 second, because we've done this 3 times and we see it's really getting closer to this value of 10 meters per second. But what's kind of neat is that calculus will let us solve that right away. So unfortunately, I would suggest grabbing a piece of paper to do part D. Okay, so for part D, it says derive an expression for the cheetah's instantaneous velocity. Guys, you won't believe how much easier this is, okay? So we had this equation that x equaled 20 plus 5t squared, remember? So calculus, when you do a derivative, what you do is anything with a variable, its exponent goes down by 1. The exponent multiplies with the coefficient, and the exponent goes down by 1. So you see how this doesn't even have a variable? It goes away. Do you see how this has a variable and exponent of 2? You bring that 2 down, you multiply it by 5, which makes 10, and then the exponent goes down by 1 unit. So this is the derivative of the position graph. So this is your instantaneous velocity equation. Okay? So what's kind of neat here, it says derive an expression for the cheetah's instantaneous velocity. Now, what I'll do is I'll throw some calc notations on there. What happened is the velocity is the derivative of x with respect to time. That's like the fancy way of writing it. And there's the answer. And if you want to rewind and try to figure out how I got 10t, remember the 20 disappeared. This is the derivative. So now what we need to do, if we want to find the instantaneous velocity at 1 second, we don't have to do that crazy stuff we just did. We simply have to plug in 1. So we write velocity equals 10 times 1. So just like I was kind of trying to imply in the last problem, our velocity at 1 second, our instantaneous velocity at that second of the cheetah is 10 meters per second. And then it says, okay, let's go further. So this is the velocity at 1 second. They say, hey, what's the velocity at 2 seconds? That's going to be really easy now. I'm not going to make you do 2 and 2.1 and 2.01 and 2.001 because that was crazy. We'll just plug in 2 for time. So the instantaneous velocity for 2 is at 2 meters per second. So you have 2 options, guys. You can learn how to take a really quick derivative to get your answers, or you can do this crazy thing here. Those are your choice.